Well, thank you, Roger. It's a great privilege to be the person to introduce this meeting. But I have to say that I only arrived very in the early hours yesterday. I haven't got much sleep, so my mind's a little bit of a blur, but maybe that's an advantage in talking about the Entropic Principle. I think my purpose is to give a general overview of the subject, and then later speakers will be talking on various issues in greater detail. Indeed, for me, it's really exciting that so many people in this audience are experts in this subject, because there aren't so many of us, and we don't often all come together in one place. So my title is Reassessing the Fine-Tunings in Physics and Cosmology. Of course, the image of the Big Bang is going to be very relevant. Now, Bernard Carr in 1974, he actually introduced what's called the Anthropic Principle. Now, lots of people don't like using the word anthropic, so it's often called the A word, but I will briefly flash there the Anthropic Principle. And I've never had reservations about using the A word, but many other people do. And Roger was referring to the paper I wrote in 1979 with Martin Rees, the Entropic Principle and the Structure of the Physical World. And that's indeed one of the first review topics on the subject. I mean, Brandon really is the person who first set the ball rolling, really. Brandon also is the person who introduced the word anthropic. Anthropic, of course, comes from the Greek word anthropos, for man. Nothing against Greek words, especially here in Crete. However, it was an unfortunate term, and I think a lot of the activity towards the Anthropic Principle really comes because it uses that word anthropic. But anyway, we're stuck with that now. And I've just included here the abstract of the paper, and many interrelations between different scales that at first sight seem surprising as straightforward consequence of simple physics, but several aspects of our universe, some of which seems to be prerequisites for the evolution of any form of life, depend rather delicately on apparent coincidences among the physical constants. And I think our paper was one of the first ones to bring together all of those various anthropic tunings. I have to say, it produced quite a polarized reaction. A lot of people found it rather interesting, and it got many citations. Other people reacted very negatively, as I say, to the very word anthropic. And indeed, I remember one well-known physicist actually coming up to me and saying he thought the idea was obscene, and getting no one in this audience, of course. And so people did react rather negatively. But what is surprising is that after all was 40, whatever it was, 79, 40, 38 years ago. But in fact, over the decades, the attitude of the community has changed. And actually, now, it's not mainstream, it's still controversial, but probably half the people in the community take the idea seriously. And that's largely because of the introduction, perhaps, of the concept of the multiverse, which gives the Entropic Principle, perhaps, a basis in physics. However, the idea of the multiverse is also controversial, as we'll see. Now, historically, I would like to start off with a reference to the meeting which was in 2001 in Cambridge, which brought together a lot of the people who are actually here today. Many of the people in the picture are also in the audience today. I won't identify them explicitly. But really, this meeting in 2001 is perhaps, again, a very important point in the history of the subject. And actually, it's interesting to reflect that that meeting was funded also by Templeton. This is a meeting, as Roger said, which is funded by the Templeton Foundation. And myself and Robert Crittenden and Martin Rees and Neil Turek, we had a grant, a cosmology and part of the Cosmology and Fine-Tuning program, and that grant actually funded 3 meetings. And the first meeting was the one in Cambridge, which I've just shown the picture from, Anthropic Arguments in Fundamental Physics and Cosmology. The second one was the meeting in Stanford, entitled universe or multiverse, and the third one was in Cambridge 2005, expectation of a final theory. And actually, it was the book, The Universe or Multiverse, which I edited, was basically arose from those three meetings. So in any case, this meeting has got a noble heritage, and I'm sure it will result in another important volume. And I'm quite proud of that book because you notice the question mark, universe or multiverse, and the emphasis is on the question mark, because we did have people from all sorts of different, including the opponents to the idea. And I think that's what's nice about the book. It does give all possible perspectives. Now, I think a nice reference to the changing attitude comes from two of the contributors. For example, Frank Wilczek says, now he made this remark in 2005 at the third meeting. The previous gathering had a defensive air, referring to the Cambridge meeting. It prominently featured a number of physicists who subsisted on the fringes, voices in the wilderness, who had for many years promoted strange arguments about conspiracies among fundamental constants and alternative universes. Their concerns and approaches seemed totally alien to the consensus vanguard of theoretical physics, which was busy successfully constructing a unique and mathematically perfect universe. Now the vanguard has marched off to join the prophets in the wilderness, because that was the case. It was really by 2005 already the subject was becoming more mainstream. And here is a quote from Weinberg, who also was at the meeting, the third meeting. We usually mark advances in the history of science by what we learn about nature. But at certain critical moments, the most important thing is what we discover about science itself. These discoveries lead to changes in how we score our work in what we consider to be an acceptable theory. Weinberg was making his comment really in the context of the multiverse proposal. And that's really why he became a keen proponent of the Entropic Principle and the multiverse. But the point I was making was that actually, if this subject is going to be respectable, you do have to change your view as to the nature of science itself. And that's an important issue, because not everybody is prepared to do that. Now, I want to put the Entropic Principle in a rather broader context, which I personally find rather useful. I'm sure you're familiar with this image. This is the image of the Ouroboros, the snake which swallows its own tail. And the point about this, around the body of the snake, you've got the various scales of structure that exist in the universe. So down at the bottom, we have human beings. As you go to the right, you have increasingly large objects like mountains and planets and suns and solar systems and galaxies, all the way to the edge of the universe. As you go to the smaller scales, to the left, you've got things like ants, and amoebas and DNA and atoms and nuclei and all sorts of subatomic things, all the way up to the Planck scale. And so you can think of this Ouroboros as a sort of measure. It's like a clock in which every minute of the clock, as you go from anti-clockwise from the top, corresponds to a decade of scale. And so that's why it just happens to have 60 decades of scale, like a clock has 60 minutes. And I like that picture because it shows how physics has come to describe all levels of structure in the universe, from the very smallest to the very largest scale. And the other thing, of course, that it tells us is that we've got the macroscopic domain on the right, of course, and the microscopic domain on the left. But the other nice thing about this diagram is that it shows the forces that work in nature and the way those forces connect the micro domains and the macro domains. So, for example, the electric force, which holds the electron to the proton, is the same force which determines the structure of solids in the macro domain. The weak and the strong forces which bind the nuclei is the same forces which power the nuclear burning in the sun. The electroweak force, which of course has been verified some time ago, that is probably in some sense going to be associated with the dark matter in galactic halos, according to some theories. The grand unified theory, the force which unifies electroweak and strong forces, that has something maybe to do with the early universe and the origin of the fluctuations through inflation and things like that. So basically, this diagram is beautiful because it shows the links between the microdomains and the macrodomains. And of course, the culmination of that macro-micro connection is the Big Bang itself. And the reason the head meets the tail of the Big Bang is, I'm sure you understand it, because when you look to great distances, you're looking back in time. So when you look to the greatest distance of all the horizon, you're looking back to when the universe was very, very, very small. And so the Big Bang is naturally contained in that image as well. And of course, we all know about the history of the universe, from the Big Bang through inflation to the Dark Ages to the current era, resulting in our observers on the right. Now, we also know, of course, that the great triumph of physics has been that it's succeeded in unifying all the different forces, electricity and magnetism combined with electromagnetism, weak forces in the electroweak, the strong forces, great unification. Still not experimentally verified, but at least theoretically a very old idea. And then, of course, the great dream is to unify gravity, with M theory being the current popular candidate. But the question you have to ask is, and of course, if you take the history of the universe and play it backwards, you know also, of course, as you go back to the early stages, you're essentially going through cosmological phase transitions where all these various unifications are manifested in the history of the universe, and many people have studied those. But of course, physicists like to think they're on the verge of the theory of everything, and that's what M theory is supposed to be. But the question is it really a theory of everything? And what's interesting about these fine-tunings is that they suggest it isn't nearly a theory of everything. It might be on the way, but it's still quite a way to go. So going back to this diagram here, of course, when we're talking about the fine-tunings, we're really talking about their relationship to mesophysics. That's the scale of not necessarily human beings, but at least the sort of complex structures associated with life. And the Big Bang, we're going to see that a lot of these fine-tunings seem to be to do with the Big Bang. So there's this sort of vertical connection between the Big Bang and mesophysics, and that's really what the nature of fine-tuning is. So to me, there's this intimate link between the fine-tunings and the Big Bang, and the link between micro and macro physics. So there we've got M theory and the multiverse, of course, which represents the, if you like, the extreme, the topmost points in this beautiful diagram. So this diagram represents the triumph of physics, but it also hints that it isn't quite as triumphant as we might think. And it also poses a dilemma. And there was an important paper which was written by George Ellis and Joe Silk, defending the integrity of physics, basically pointing out that you have to assess very carefully whether something like M theory and multiverse, whether these are part of conventional physics. Now, I do have a somewhat different view. I mean, I defend the role of M theory and multiverse as part of science more than they do, but the point is, it's the issue which is so important, and it's an issue that science has to grapple with. Because, as I said before, science certainly has to change if it's going to accommodate these sorts of questions, and how much it has to change is the sort of issue. Now, so let's get on to the anthropic principle. I always start off by distinguishing between the anthropocentric view, that man is the center of the universe. Sorry to use the sexist word man, because that's anthropos is the word for man, but I'm afraid that's in my slides because these are quite old. So human, I should say, I'm sorry. But that, of course, was soon demolished, and we had the mechanistic view, which says that the universe exists independent of our awareness of it, the Newtonian laws of classical physics. Just go on regardless, so that's my image of the mechanistic universe. And then there's the anthropic view, which says that some features of the universe in some sense are explained in inverted commas, because no philosopher is going to like that word if I don't put inverted commas there, by the requirement in some sense that life and mind should exist. Now, a lot is going to hinge on precisely what is it that is required. Is it life, mind, or certainly not just human beings? I actually, it may have something to do with observers, but I prefer to think of it as the evolving complexity view. If it had been me, I would have called it the complexity principle, because to me, the crucial thing is that Big Bang should lead to an increasing order in the universe, increasing levels of complexity, and to me, mind is in some sense just the combination of that. So I think if Carter had used the word complexity principle at the outset, we wouldn't have got bad press. But then I want to stress, this is a meeting about fine-tunings. And there are many different sorts of fine-tunings in physics. And some are more respectable than others. So I thought it would be useful just to start off by making this distinction. Some of the first point to make is that physics itself implies natural relationships between the various scales of structure, which at first might surprise you, but actually, when you think about it, they're not surprising. And in the original paper with Martin, we wrote down, we showed how all the scales of structure in the universe, like the universe, galaxies, stars, Jupiters, humans, protons, planets, can all be expressed in terms of various constants, in particular the proton mass, the atom size, the fine structure constant, 1 over 137, which is the strength of the electric force, and the gravitational fine structure constant, which is a very, very small number, 5 times 10 to the minus 39. And our point is that when you look at the macroscopic world, as opposed to the particle physical world, everything in nature, to an order of magnitude, has a scale which is determined by alpha and alpha g. And that's straightforward physics, nothing controversial about that. But then that gives rise to various coincidences. For example, the size of a human being is roughly the geometric mean of the Planck scale and the scale of the universe, which is precisely why human beings sit at the bottom of that cosmic Ouroboros. And there's nothing mystical about that, it just comes out as straightforward physics, but it's not obvious. And then there are various other things. For example, the number of stars in the universe is roughly alpha g to the minus a half. Alpha g is obviously the dominant term here because it's so tiny. The number of galaxies in the universe is alpha to the minus 6. The number of stars in the galaxy is alpha to the fourth, alpha g to the minus a half. So there are all sorts of interesting relationships between the scales of structure, which are part of natural physics. And I wouldn't call that fine-tuning, but it is a sort of coincidence which you might misinterpret if you didn't know about it. And then there are the what's called the weak anthropic principle, which is merely saying there is a selection effect for when and where observers exist. And I would say this is also completely non-controversial, even though it does contain the A word. It's simply a logical necessity. We know, obviously, that we have to exist in certain places in the universe, close to a sun, and we also have to exist in certain time. And this is the famous argument, why is the universe as big as it is? Well, the size of the universe is, when I say the universe, I mean the visible universe, and that's simply the time since the Big Bang, which is about 14 million years ago. A mechanistic view would simply say, well, the time since the Big Bang is 10 to the 10th years, so the size of the observable universe is 10 to the 10th light years, roughly, about 1.4. And there's no particular reason for this. However, the anthropic view came from Bob Dicke in the 1960s, and he said, well, life requires heavy elements which have to be made in stars, so there would be no life before the time. Some stars have to explode, and therefore you have to wait at least for the time scale of a star, which is roughly 10 to the 10th years. Of course, there's really a huge range in the lifetime of a star, but for a solar mass star, it's roughly 10 to the 10th years. If you wait much longer than that, then of course all the stars will have burnt out, so there won't be life either. So the point is, on this argument, life can only exist in a small window of time, which is something like 10 to the 10th years. Of course, it's not saying the universe can't exist outside that time, it's just saying we wouldn't be here looking at it. So, and that explains the coincidence that the age of the universe is, roughly speaking, the lifetime of a star. And incidentally, in terms of straightforward physics, the lifetime of a star is alpha g to the minus 1 times the proton time scale, which is 10 to the 10th year. So that involves this number alpha g to the minus 1. And so that's quite a purely, I would say, rational requirement. But then we come to the Stronganthropic principle. And that's saying there are fine tunings between the constants of physics themselves, which are needed for observers, but not predicted. Now, I have to warn here that the word Stronganthropic principle is used in different ways. This is the way in which Carter used it, and it's the way in which myself and Martin Rees use it. Later on, people like Barrow and Tipler, they use the word Stronganthropic principle in another sense, to say, in some sense, the universe must be such that life exists. And there's quite a lot of confusion in the literature. I'm sure other people will refer to this about what we mean by Stronganthropic principle, but this at least is what I mean. And of course, if you believe in the multiverse, then of course the Stronganthropic principle becomes an aspect of the weak anthropic principle. But that, of course, merely pushes the buck one step further, where you believe the multiverse is respectable. Now, let me give you some examples of this, because, well, what are the constants? This is a list of a large number of physical constants, and some of them do with particle physics, and some of them have to do with cosmology. And so you have to ask the question, well, which of the constants are fundamental and how many are independent? Because we know our final theory is going to relate some of these constants. So if you're going to say some of the constants are fine-tuned, which ones are we actually talking about? And conventionally, the first thing one does is to focus on the dimensionless coupling constants. So these describe the strengths of the four forces of nature: the strong, the electric, the weak, and the gravitational force. I've already talked about the gravitational force and the electric force. The strong force has got a coupling constant of 10, and the weak force 10 to the minus 10. I've not defined very precisely what I mean by the coupling constant, but this is how we define them in the paper with Martin. And the question we have to ask is, well, will the final theory of everything, whatever it is, explain these values? Because at the moment, none of these values are explained by our final theory of physics. We don't know whether these parameters are going to be contingent or whether they're going to be uniquely predicted. A lot of physicists would like this to be uniquely predicted, but we've no evidence for that at the moment. Now, why do I say, though, that it might be an anthropic factor here? Well, I'm going to give some of the examples. These are the examples coming from the original paper with Martin. That's why I call this the Entropic Principle Revisited, because I'm revisiting the original anthropic relationships. Now, it comes from straightforward physics that a star has got a mass of something like alpha g to the minus 3/2 times the proton mass. I mean, that's the mass of the sun. I mean, obviously stars have a range of masses, so there's always twiddles in front of these things. But a much more subtle thing is there are two different types of stars. They're stars where the heat gets basically to the surface through radiative processes, a radiative diffusion process, and there's the stars, the smaller stars, through which the convective processes are important in getting the heat from the core to the surface. And that turns out, again from fundamental physics, is another combination of alpha g and alpha and alpha. And the only reason that stars actually encompass both convective and radiative types is because of this remarkable coincidence that alpha g is the 20th power of alpha e. Now, obviously, that's true because the 20th power of 10 to the minus 2 is 10 to the minus 40. But the point is, it needs to be true if you want convective and radiative stars. And this is just some planets being born in the Griffith Nebula, the Eagle Nebula. But the point is this, that you need to have some stars which are radiative, because you need to have that for the onion skin model, which is associated with supernova. And then it's thought that the stars which are convective, they're the ones which might be associated with planet formation, for reasons which are a bit too technical to go into. You do need both types of stars in the universe, and you could argue both of those conditions are necessary for life. Supernova, so you have elements, and planets, so you have people. Obviously making assumptions about whether life requires elements and planets. But the point is, this relationship is required for life, but it's completely unexplained by physics. And Page later looked at this in more detail, and he argued this constraint was accurate to something like 3%. Recently, Page has actually gone a bit overboard, I would say. He might have seen the paper he produced recently where he uses this relationship. He finds that everything E is the electric charge, and in Planck units, that's basically the square root of alpha. Okay, so he shows that everything in the universe, I mean, all these fundamental constants like the proton mass, the electron mass, the age of the universe, can all be thought of as powers of E. Okay, but he wrote that just as an empirical result, first of all, and then he points out, which I did find rather interesting, then there's the cosmological constant, and this just seems like playing around with numbers. But the point is, the Carter condition, which can be written in this form, does actually imply those expressions, and which is sort of interesting. If you believe the Carter, you get these enormous powers of E coming in, and then the other thing is that there's also a renormalization group argument which relates alpha to the proton mass. In fact, this is to do with the fact that alpha is related to the logarithm of alpha g quite naturally. In fact, we even pointed this out in the paper in 1979. So now Page then gets this very precise relationship between E squared log NE, which is meant to define basically the on structure constant, and then he claims that, and it is, all these things are accurate to a few percent, apparently, and then you get everything else like the mass and radius of the Earth and the AU and the day and the year all comes out in terms of E. Now, I must confess, I was a bit uncomfortable reading this paper because it's a typical example of how you get obsessed with numerology. But nevertheless, it does sort of come out, and yet you've got to be aware that once you start talking about these anthropic students, you do sort of start going in this direction, which makes some people uncomfortable. But I thought it's still quite interesting. Now let's go back to the my favorite diagram, the Ouroboros. If I can write down these scales in terms of the value of alpha g, and so all the scales are powers of alpha g, that's straightforward physics. And so you remember I pointed out that the 60 decays of scale, and the reason for that is that alpha g is 10 to the minus 40. And therefore, alpha g to the minus 3/2, so that's the scale of the universe, is 10 to the minus 60. But that, of course, raises the question, why is alpha g so small? Okay, because if alpha g wasn't 10 to the minus 40, this Ouroboros, you could still draw the Ouroboros, it's just that the number of decays would be much less. So why do we need alpha g to be so small to have life? And, well, there are various arguments. For example, according to Dickey, the age of the universe is alpha g to the minus 1 times the proton timescale. That's the lifetime of a star. And so if you think life is going to take a long time to form, alpha g must be less than the ratio of Tp to the time for life to form, which is obviously going to be much, much less than 1. Another argument is you can say, well, presumably the probability of life forming in any stellar system is small. If that probability has some small value, then we need the number of stars in the universe to be large, and therefore the number of stars in the universe, again from straightforward physics, alpha g to the minus 1/2, we need that to be bigger than p to the minus 1 to have life somewhere, so alpha g again has to be small. So there are qualitative arguments why you might think alpha g has to be tiny for life to exist. Now let's go back, let's talk about another constant, let's talk about the weak fine structure constant. Now, we need, of course, supernova in order for the elements made in the stars to get disseminated through space. The only reason supernova work is, roughly speaking, alpha g is the 4th power of alpha w. And physically, I won't explain how that formula comes, but it's in the original paper in 79. The basic idea is that when the star collapses, it produces a surge of neutrinos. The neutrinos interact with weak interactions. If the weak interaction was too strong, they'd get trapped in the middle of the core. They wouldn't be in a supernova. If it was too weak, they would go straight through the envelope and the star wouldn't explode. It's only because of that remarkable tuning that you actually have a supernova. Now, rather remarkably, exactly the same relationship explains why you get an interesting amount of prime helium made in the Big Bang. If alpha W was too weak, you would get no, because the weak interactions determine the neutron-proton freeze-out ratio. And if that relationship wasn't satisfied, you'd either get 100% helium, which might not be good for life, there wouldn't be main sequence stars, main sequence time stars, or 0% helium, which probably wouldn't be a problem then, actually. And in fact, the same coincidence is also related to why the baryonic density and weak dark matter have got to have comparable densities. This was an old paper I wrote with Mike Turner way back in 1978 or something like that. So this coincidence crops up in quite a number of different ways. Of course, not everyone believes in weak dark matter nowadays, but again, this relationship is required for life. If you think supernova is required for life, but unexplained by physics. Then there's the famous triple alpha coincidence, which was pointed out by Hoyle. How do you make carbon, which is again here assumed to be a basis for life? Well, it goes through two stages. First of all, you make beryllium, and then two alphas combine to make beryllium, and then you combine with another alpha to make carbon-12. And that's how you're meant to make it. Now, the only trouble is that the beryllium is unstable, and that process only goes through because there is this remarkable resonance, which is means an enhanced cross-section for production of carbon. And Hoyle pointed this out in '53 before this resonance had been discovered, and he told his friend Willie Fowler to look for it, and he found it. So beryllium would decay too soon, but for this finely tuned resonance. And then other people have looked at this. I think Maria Livy's I think it is one of the people who first looked at this, and I think the most recent paper will argue that the strong fine tuning is it has to be tuned to something like 0.1%. Now, some people say this is even regarded as an anthropic prediction, but I know that's somewhat controversial. But in any case, this is what Hoyle convinced Hoyle that the universe was a put-up job, as he put it. Well, not all Hoyle's ideas were correct, but lots of them were. So, what about the constraints in chemistry? There's huge literature on this. We're talking now about alpha S. If alpha S was increased by 2%, all the protons would go into diprotons at Big Bang nucleosynthesis. There'll be no hydrogen burning stars, and therefore perhaps. Well, I was told I don't know time for life. If it was increased by 10%, all protons would go into nuclei of unlimited size. There wouldn't be any interest in chemistry. If it was decreased by 5%, neutrons would be unbound. You'd only have hydrogen, and again, maybe no interest in chemistry. So these are the constraints you can't really see, but it's alpha and alpha S on that diagram, and we just have to be in this little white. Well, that's where we actually are, in that little dot. We have to be in a very small region. There are other constraints involving the masses. The electron-proton mass ratio is 10 alpha squared, which actually I have used in the previous slide. The neutron-proton mass difference is about twice the electron mass. So there are lots of these constraints, and they're discussed by various people. Nowadays, of course, we would interpret these not in terms of the neutron-proton masses, but in terms of the QCD parameters. So this is expressing things in terms of the quark masses and the electron mass, for example. This is from Craig Hogan's paper, but basically the same idea. The fine tunings get turned into QCD relationships. Now, I have to say that these arguments about stars and chemistry, I've been rather blatant in simply saying this requires fine-tuning, but I have to say Fred Adams has played a crucial role here in actually questioning that and asking how fine-tuned actually do these parameters really be to have stars. And there's a whole series of papers that Fred wrote, I mean, showing how you can't really see it, but this is a diagram of basically alpha G against alpha, and how you have to be in, it all looks invisible, but you have to be in this little region here if you do a broader calculation. And I'm assuming, Fred, you will talk about this. Yes, so I don't have to say much about that. And also, I would also like to highlight the word of Luke Barnes, who's recently, for example, written a very interesting paper about the importance of deuterium production in stars. And I have to say that Luke has also co-authored a very nice book on the whole topic. Oh, sorry, and you're even in the audience. Sorry, so. Oh, I do apologize. Yeah, I got it right in the crowd. I do apologize. Yeah, but anyway, yeah, brains crop up everywhere in this meeting, I'm afraid, but it's great. And anyway, so well, thank you both of you. I read your book on the plane coming here, I should say. Then for our final, there's a whole host of cosmological parameters, and these were highlighted in Martin Rees's famous, well, popular book, Just Six Numbers: the ratio of the electric and gravitational forces, the strength of the nuclear forces, the matter density, cosmological constant, the amplitude of the fluctuations required to make cosmic structures, and indeed the number of spatial dimensions. So these are constants of physics in some sense. These are constants associated with cosmology. And again, your cosmologist like to think he's going to be able to predict these values, but in some sense, all of these parameters could be contingent. So let me go through these briefly. I'm assuming, Roger, can I have till the full? Yes. Is that right? Because I know there's a general discussion at the end. I mean, I've just timed it for, okay. The density parameter. Well, even in 1979, we knew omega had to be close to 1, because if omega was much bigger than 1, the universe would collapse before the timescale. Between the timescale of a star. If omega was much less than 1, the fluctuations never freeze out. So even in those days, we knew omega had to be less than, pretty close to 1. Nowadays, of course, we know omega is 1, or close to 1, because of inflation. We didn't have inflation in 1979. But inflation itself requires fine-tuning, and I imagine someone else is going to talk about that later. The photon to baryon ratio, of the most important parameter in cosmology, of 10 to the 9th, that's also constrained in all sorts of ways. If you want the universe to be matter-dominated before the Dicke time, which we obviously do, that says that S has got to be less than alpha G to the minus a quarter, which is about 10 to the 10th. On the other hand, if we want the universe to be radiation dominated at Big Bang nucleosynthesis, that says that S has got to be bigger than some value which depends on alpha W to alpha G, which turns out to be 10 to the 4th. So again, that's if you want a normal Big Bang nucleosynthesis. If you nowadays it's assumed that S probably reflects some barrier symmetry before 10 to the minus 5 seconds. But in most gut models, the expected value of S is some negative power of the alpha x, the unification coupling constant, which is something like alpha G to the minus a quarter. Well, we know that this has got to be something like alpha G to the minus a quarter there, and that actually is naturally the case if alpha G, that says that alpha G has got to be less than alpha to the 4n. So in fact, even that comes out if n, for example, had a value of 3, n is just some integer. Now, of course, the convective star condition comes out from n equals 5, not n equals 3. Amplitude of the fluctuations, well, if we know if that's Q at the horizon epoch, we know if that's less than 10 to the minus 6, the gas cannot collapse into gravitationally bound structures. On the other hand, if it was bigger than 10 to the minus 3, you'd get lots of black holes forming. Here's a rather nice diagram taken from Luke Barnes again. And the point is that Q has got to be finely tuned. We know, in fact, of course, it's about 10 to the minus 5. So there where we actually are. And there are various physical conditions. For example, this comes from lambda 0 from Tegmark and Rees. But then maybe the most famous anthropic constraint of all is to do with the And the point is, I should say that Q has to be close to the boundary in order to actually, there is Q, we have to be close to this boundary if it's really the reason for this fine-tuning. But in any case, it sort of can be explained by anthropic arguments. And then the most famous one of all, of course, is the cosmological constant. I know we talked about why in principle, the cosmological constant could be anywhere from minus the Planck density to plus the Planck density, but in practice, we know it's very, very tiny compared to the Planck scale by 120 orders of magnitude. It's 10 to the minus 56, I suppose, 10 to the 66 units of centimeters to the minus 2. And the famous argument from Weinberg is that galaxies can't form if omega lambda is, unless omega lambda is less than about 0.6. And this also constrains actually combinations of lambda and Q. And so this is really very important in terms of the development of the argument, the anthropic argument, making the anthropic argument respectable, because in some sense this is what got the particle physicists interested. Because as I'm sure you know, in the string landscape scenario, you expect a huge range of vacuum states. And the question is, why are we in a very narrow range of possible values for lambda? And the argument given by Weinberg originally is that the anthropic argument is the only one that seems to explain this. And so I took all these quotes from Barnes's paper. I mean, well, I don't have time to show them all, but and Linder and Vankren, the anthropic principle is the only known solution to the cosmological constant. Well, it's not really as simple as that, because there have been plenty of other people who made explanations. But the point is that at least that is the feeling of quite a lot of people, and that's why so many particle physicists have got excited by the cosmological constant. That's why Weinberg became an advocate of it. And now, so I've got to begin to close up. I want to just say this is the dimensionality of space. Mark looked at the number of time and space dimensions, and in some sense, there are anthropic reasons why we have to have 3 dimensions of space and 1 time. How that arises, whether it naturally arises through compactifications of extra dimensions in M theory is a big topic, but at least that there is an anthropic constraint. Life cannot exist for various reasons outside that little white square in the bottom. And then finally, there are anthropic fine-tunings, which are cool fine-tunings. A famous one is to do with the Higgs mass. The Higgs mass, 125 GeV, it's the geometric mean of the dark energy mass and the Planck mass. The dark energy, the lambda cosmological constant, has got this natural mass scale associated with it. And we know that there is a fine-tuning involved there if the universe is to be stable, and that's where the Higgs mass actually is. But we don't understand why it has that fine-tuned value. But it's not clear why that's got anthropic significance. So in fact, Wilczek in his chapter in my book has got a nice classification of all the different sorts of tunings. I've got no time to go into this diagram, but the sort of anthropic tunings are just one of the 4 quadrants in this diagram, but let me just miss that out for the time being. Okay, so I've got to really begin to end. I will just end by giving you the opinion of people. Now, let me, I'm not going to give the opinions, I've run out of time, so let me just quickly go on to my final slides. What counts as an observer? I know this is going to be talked about later on. It really isn't to do with humans, I should say. Is it a human? Is it a mouse? Is it a robot? Is it a photon? I mean, in physics, it simply is not a well-defined question. And as I said, or is it something to do with consciousness? My own view, as I said, is that it's actually to do with the pyramidal complexity. The development of complexity, which has occurred during the Big Bang, has only arisen because of these fine-tunings, which I've talked about. Now, and the precise criteria may not be crucial, because in some sense the pyramid may inevitably culminate in mine once it starts to arise. In other words, we're building up from quarks to protons to molecules and organisms. And in some sense, we have brains at the top. And to me, that's just a part of the process of the complexity building up. So to me, the complexity is probably the crucial feature of this. And this is a summary of all the fine-tunings required for the Big Bang, which I've gone through. I mean, the point is, in assessing the fine-tunings, it really comes down to how many there are and how fine is the tuning. And then I must then, if I can just go into negative time, I must end by talking about the explanations for the fine-tuning, because I'm sure this is going to arise in later talks. Essentially, you've got three sorts of explanations. The multiverse, my favorite. You've got the more mystical idea, which goes back to Wheeler, and the idea that quantum theory, the collapse of the wave function is induced by consciousness. So Wheeler said, well, maybe the Big Bang evolves life, and then we look back and we contemplate the beginning of the universe, and that's sort of closed circuit. So consciousness, in some sense, brings the universe into being. And then, of course, there's the explanation which physicists really hate, which is that it's something to do with God. You imagine you've got this parameter space, and you fine-tune. God puts his pin in just the right place. Now, obviously, multiverse is in the domain of physics. Consciousness, most people regard as being in metaphysics, and God is clearly in the domain of theology. And by and large, of course, physicists feel uncomfortable going into metaphysics, and they feel sort of uncomfortable squared going into theology. And that's, I think, why physicists actually were so negative about it, because it smelled of God. Physicists don't like that, even if they're religious. And so I have to say, though, that even the multiverse is controversial. I mean, because a lot of people don't think that's respectable physics either, so they would put the multiverse into metaphysics, maybe Wheeler into theology, and this is the idea that the universe created itself, the creation of the Many physicists would prefer that. One universe, nothing to do with consciousness, nothing to do with God. My own view, I've had this debate with George, and my own view is that there is a boundary between cosmology and metacosmology, which is constantly evolving. Okay, and that it's always been the case that the frontiers of cosmology is in the domain of philosophy. That's why our last meeting was on the philosophy of cosmology. Today's metacosmology becomes tomorrow's cosmology when the data arises. And so the boundary between them is evolving. And so I, in some sense, accept with George and perhaps with Joe that today we should regard it as metacosmology, but I think in principle the evidence may come in that makes it respectable cosmology, but it should be data-driven. George Asattu said, such ideas may sound wacky now, just like the Big Bang theory did 3 generations ago, but then we got evidence that it changed the whole way we think about the universe. And really that summarizes the whole history of the Big Bang. Ideas are regarded as metaphysics, and then they become physics when the data comes in. And I've overshot my time, but I think that's I think where I had a list of objections to the Entropic Principle, but I'm not going to go into those. I think I'm just going to end at that point. Sorry for overlooking. Okay.
Thank you very much for making such a broad canvas. It's hard for me to imagine small questions on this topic, even if there are a couple of clarifications. So you mentioned 3 explanations. What do you like? Sorry.
Yeah.
Sorry, Bernard, you mentioned 3 explanations for fine-tuning, but isn't there a 4th? Namely that we've only been thinking about these problems for rather a short time, relatively speaking, in science, and couldn't we expect, whatever, in a century or whatever, some new theory which most likely would give a physics explanation for all these fine-tunings?
Well, I mean, actually, you give me a chance to put up my final slide, but let me just answer this. I mean, a lot of people say, well, maybe the final theory, or whatever the final theory of physics, will explain, will explain the values of these constants. But then the point is, but then it still remains a remarkable coincidence that the final theory predicts the values which are required for life. So, of course, a lot of physicists would prefer the values to be predicted uniquely, But at the moment, it doesn't look like that. And if it is true, it still will be a remarkable coincidence. But there are other explanations. I mean, which I haven't gone into. Paul Davies has this idea that, you know, the laws of nature evolve in such a way that life can arrive, which is sort of somewhat intermediate to it. Yeah.
Bernard, it's a beautiful talk, but there was a basic assumption there. You say the strong anthropic principle becomes the weak anthropic principle in the multiverse. You're assuming that your multiverse will contain universes that allow life to exist. Why should that be true?
Yeah, I mean, well, there were a lot of hidden assumptions in that remark. I'm assuming, first of all, that there is a multiverse. I'm assuming that in the multiverse the constants can vary, and which is an assumption because we don't know in principle that the multiverse. But I'm also assuming, of course, that that there is actually life somewhere, which is, I think, the point you're getting at. I think that's true to some extent. I mean, the assumption in all of this is that if you've got this parameter space for all the parameters, you know, the parameters which are relevant, we're always assuming that there is a small fraction of the universe, of this filling factor of this parameter space where life can arise, and it doesn't fill all of most of the space. But we're also assuming it has to be there, so it's neither 0 nor 1 in some sense, the filling factor. So I agree in principle with that point, but that nevertheless, I don't think that's invalidating the statement that you may need. You're getting down to the question of whether it's a proper explanation, but it doesn't. But all I'm saying is that it in principle allows you to have, in some sense, but it may be a necessary delay.